Eric. Eric's one of my former coworkers. He's been architect of several different sort of video DSP chips for Video Locus, LSI Logic, Magnum IDT. He has deep, immense knowledge of video codecs and sort of hardware architecture. So take it away, Eric.
Okay. Thank you, Chris, and SSIM for hosting this meeting. I really appreciate it. And as well, thank you for Ahmed and Robert's presentations. I found them very informative. Let me share my screen here. Let me see if I got the right one. You should be seeing a splash now.
Yep.
Okay. I want to drag you a bit down, down into the silicon muck a bit. Let's talk about open source hardware video encoder. Myself, I am a bit of a field programmable gate array evangelist. I love these things. The amount of wire wrap time it saves is incredible. I have a background in hardware engineering with specializing in video, codecs, imaging, and crypto. Back in January at this same meeting, I did a deep technical dive into the MPEG WebVC video codec. Basically, because I was honored to be an editor of that standard. But I look at it, and the reason I joined that effort was it's the lowest common denominator of H.264, basically the constrained baseline spec, but it's a standalone spec. So I found that interesting, and at that point, I proposed an open source hardware project for it. You know, it's not the only H.264 hardware video codec out there. I'm sure there are many that I haven't even seen. But what I wanted to focus on was low latency, which I felt, and throughput, which I feel really show off what FPGAs could do. So I'm proposing a 1080p hardware WebVC video encoder project, and using the AWS F1 FPGA platform because it means everybody can get access to it, as well as it's it's for an experimenter like myself. It's very reasonable, very affordable, right? For example, I've been doing development on it, and it costs about $1 a day if you're doing interactive synthesis. That's quite affordable. For low latency, another reason for low latency is honestly, VQ is a bit less of a differentiator at the high bandwidths associated with low latency. So I've structured the codec as a column refresh with a long-term gray reference entry stub, if that makes any sense. So I have actually made progress on this, and so I just wanted to share today. Let me just switch gears here. Next, there's only a couple slides here, so I'll just switch over to the diagram. Everybody likes looking at little diagrams. So what I've got so far and progressed a bunch on is I've got a C model up and running of the encoder, and in particular, I feel that the core transform block processing engine is a secret for a highly efficient H.264 encoder. So basically, I've coded up the block you see there, the H-shaped blocks, is the core transform encoding block, and with 27 cycles through that block, you can code a macro block. I've progressed and got it up and running, the block by itself up and running a simulation. Verified a little bit against the model, certainly not complete, but enough to give me some confidence in my area numbers. How big will this hardware be? That one block, the transform block, and that one will be about 30,000 LUTs, or about 5% of the available logic of the F1, which is a AWS FPGA that you can rent. And so it's quite compact at this point, and I feel that I can, that it can actually make a useful encoder. So what I proposed is really not a full-fledged encoder. I know what a real codec development takes, and that takes teams and some significant effort. But I wanted to go forward and what's the minimum viable 1080p encoder I could do. This is the architecture I've come up with. I've got Verilog. You can sort of see I've got coded up the central blocks, coded up the lexicon, and as well as some of the DMA and buffers type logic, and it's moving forward there. And so I'm trying to move towards a 1 millisecond latency 1080p encoder. And there's lots of ways of measuring latency. Like, you know, the true purist says it's glass to glass. I That's something I can't really control because I can't control the camera, I can't control the transmission, I can't control the decoder. So I put it as something that I would find most useful as a system architect, which is 1 millisecond latency from the availability of the frame till all the coded video is available. So you give a pointer to a frame, 1 millisecond later, you have encoded video for that frame. So I still have a few things to do though. There's for some reason, I'm stumbling on the emulation prevention block. You know, it's sort of the 0.3, so you don't start code to emulate. But because I'm working on such a wide data structure of like 64 bytes per cycle, that one's causing me some thought. I would have to build up my rate control block. So if you sort of see here, this is really a dual pass encoder in terms of you pre-encode before the lab, every macro block, get its rate out of it, and then you post-encode later, adjusting so that over your LAB buffer, which in this case I've chosen was 120 macro blocks for one row, that you've met your, basically you haven't exceeded your max rate. So capped VBR, if you set your rate low enough, really acts as CBR, but if you set your rate high enough, which is where I anticipate this is going to go, this will be used, it will just run in CBR mode when the rate gets too high. So I've got to, you know, I still have to yet to do the C model and Verilog for that, as well as a top level integration I've shown here. And really that integrates into the AWS HDK shell, which is the environment they give inside the FPGAs on AWS, which provides me the things that I don't want to spend time on, like PCI Express connections, the DMA to the host memory, and as well the DRAM controllers. Next step after that will be to do a full chip synthesis and do hardware bring up on the AWS F1 and run it at whatever speed it can, right? Because the main block I've done there is still combinatorial. And then at that point, to get my speeds up, it starts pipelining the transform core. And what its area impact will be is it remains to be seen, and whether there's some problems there. But my target rate is 250 megahertz, which I've done in the past many times. And with that, that would give me a 1 millisecond 1080p frame. You know, frame throughput, frame latency, I get confused sometimes. Then after that, really what's missing is direct host access. Rather than using the FPGA memory, just go to the Intel's host memory to grab your input images in 422 raster format or whatever is available. After that, I could sort of see, you know, I would sort of, that's where I want to sort of, I'll be able to call it complete at that point. Really, the roadmap there from there on is get some open source project quality. I'm humbled by the vast open source projects I see out there, and you know, I'm going, how could I ever get there? But I feel that by you know, providing something that's slightly new, it might be of value to people. And so you know, as I have time, up the quality of the open source, you know, the documentation, the guides, the scripts, the release. I'm running under GitHub now with the MIT license, but that may change. You know, probably need some legal advice. And then some ease of use steps. We've heard FFmpeg mentioned today, you know, or same with on AWS. AMI images make your environment very easy to use, or perhaps containers are applicable. And then, you know, it's really a matter of, at this point, it can run on AWS F1 easily, but we start porting it to other platforms. And in fact, one of the ones that I know is very useful is the Xilinx Vitis platform. It used to be called SDXL, but that enables a rapid port to all sorts of other clouds as well as boards, you know, and there's a certain amount of these mining boards, which many of them were FPGA based, are now coming available and may be affordable by the individual hobbyist. The real one I'd like to do is my background, you know, is there's no real AI inference in my background. I'd like to ramp up a bit on that. And so the Vitesse infrastructure includes an AI kernel. And I'd like to see if I can apply that to ROI QP modulation. So basically, if there's something interesting, ramp up the bit rate for that region of interest. And then one of the things I haven't really mentioned, well, I mean, is VQ. There's always room to improve VQ. You know, so far I think with minimal VQ and high bit rate, not as important, but there's certain value, and I think I could invest as much time as I wanted. And you know, Next thing would be add motion estimation, better motion estimation, adaptive quant, RD-opt. You'll see the structure here is very easy. If you replicate these H blocks, you actually get an RD-opt encoder, right? So far I've got it simple to choice between your final decision, PCM, or skip. And one of the things I really know the spec inside out, and I wanted to avoid the corner cases at high bit rates. You start hitting some interesting cases where your bit stream becomes illegal, such you only have 3,200 bits per macro block. But this is complicated a bit by, because each transform block, I think I counted this right, can produce about 497 bits per 4x4 transform. So you have to add up the bits for the entire macro block, see if you've exceeded them. As well, there are transform overflows that start happening. H.264 is spec for using a 16-bit math inside of its transforms, and says you shall not overflow. So here I can actually test while I'm transforming to make sure I don't overflow and have a backup plan. Similarly, there's things on maximum coefficient size, and what else is there? There's, well, there are a few other little gotchas there, so I want to watch out for those. Let me go back to a previous slide here. I think I've covered it all while looking at the diagram. So I am moving forward with this, and if you'd like to talk about FPGAs or low latency encoders, feel free to get in contact with me. I'd like to thank you for your time, and if there are any questions for this quick update, feel free.
Thanks, Eric, for the talk. It's always great to hear you talk about low-level codec related things. So open it up to the floor. If anyone who has any questions, just unmute yourself or type into the chat.
And thank you for your time and the opportunity to present here. I appreciate it very much.
All right. Thanks, Eric. Thank you, everyone. I guess this concludes the, I would say, fairly successful first KW Video Tech Meetup online. Plan on doing this again next month. So if you're interested in talking, or if you know someone who's interested in talking, let me know. Join the group. You can find me on Video Dev, Slack, or contact me on LinkedIn. Yeah, if you have any questions, we'll be sharing this this meetup online on the KW Video Tech YouTube channel. But yeah, so thanks everyone, and